recording this. So yeah, so one thing I just want to show you is there's a handouts page now. And like the sets handout we had, and actually we're going to look at, I think, all of these today. Well, the notes on quantifiers is just sort of my notes outline for what I'm going to talk about. But yeah, so there's that handouts page now, and then under the, I'm trying to sort of put some more like what we're going to do. I still need to go back and actually put the lectures in the old class meeting pages so that people can look back at them if they want. I got behind on that, but I'll go try to do that. And so, yeah, so we'll just be doing this stuff. I mean, I guess I could just leave this on screen if you want. You can see where we're going with it. I just sort of wrote an outline for myself. Remind myself of stuff I want to say. So, okay. Oh, by the way, okay, so yeah, so I want to talk about quantifiers today. And I actually made about a sheet of the axioms for the integers, like it says on the handout, but we can also just write some stuff down and I can show you. But yeah, so quantifiers. So there's sort of a certain structure to all mathematical statements. I mean, I mentioned like, you can almost reformulate everything to be about a set or a map between sets. We'll see that when we get to functions. And every time you talk about an element of a set, you want to quantify it. So let me just give you a couple examples. So we have something like for all A, B, in Z, A plus B equals B plus A. So what we said here is the for all, like for every choice, for any choice. We could say for all, for any, for every. But when we introduce these variables, we don't just sort of say A comma B and Z, A plus B equals B plus A. We actually say like, what we're actually making a point here of saying that we can choose anything, right? Like this is a quantifier. And this is actually called the universal quantifier. So it's basically saying like, I can choose, basically I have a set and I'm choosing any random elements of it. So I can, for all, so universal because I can choose anything. Okay, so i.e. choose any element of the given set. So that's called the universal quantifier. There is a notation in math for this. It's this upside down A you might have seen. So it's like that. So we really read this as for all. Actually, the LaTeX command is / for all. So that tells you how to read it, right? This upside down A. So that's one example. And we had a lot of this, right? All of this sort of like, all the like associative, commutative, distributive, those all had like a for all in them, right? Actually, maybe I should show the axiom sheet for the integers here. So yeah, actually, I'll talk about the sheet more later, but 0 through 6 is what we basically talked about. 0, I didn't really say that explicitly, but like some people like to state closure as an axiom. Sorry, okay, yeah, so some people like to state that basically addition and multiplication are well defined, that like if you take two things in the set and add them and multiply them, you're still in the set. But right, so we have, I guess given could also be like, we actually said given any A and B. Here we have for all, for all, for all. Here's a for any, for any, for each. They're basically all versions of the same thing. You mix it up a little bit so you don't sound robotic, but basically, so yeah. So anytime you see yeah, for all, for each, I guess I should, for each, for any, or given any, yeah, okay. And then another example, stop the share. So another example would be the existential quantifier. Those are the two main quantifiers, the universal and the existential. So the existential quantifier is if we want to specify a particular element of a set. So you could say something like, there exists, oops, I already wrote the symbol. There exists, or there is, let's say B in Z such that, for all A, usually a lot of times there exists comes before us, for all A in Z, A plus B equals A, right? And we know the specific B we're talking about here. I guess I wrote it a little bit differently up on the axiom sheet there. Like, there exists an integer denoted 0, which acts as an additive identity. So, right, namely B equals 0. So that's the additive identity. And so here is there exists. And so this is the existential quantifier. So that's like saying I'm claiming that within the set we're looking at, there's a specific element that does a specific thing. There's always a such that after there exists usually, because like you're trying to specify what specifically you want to say about that element, like it exists for what purpose, So existential quantifier. So this is like picking out a specific element of a set. Or claiming that you can pick out a specific element with a specific property. Specific element. A set. And the notation here is this backwards E. I actually don't even know where those come from now that I think about it. The backwards E, and actually the LaTeX command is \. I think it's exists. I think it's not. I think it exists with an S on the end. So, I mean, there's a funny thing with the shorthands, the upside down A and the backwards E. When I'm typing math, I almost never use those symbols. It's not much harder to just type the words for all, there exists. It's more like when you're writing on paper or on the board or something, and you just want to be as compact and concise and lazy as possible, that you start writing things with much more symbology, But if you're trying to actually present mathematics, like I don't see math papers that have like upside down A's and backwards E's in them and stuff. You might as well just type the words out. So notice I didn't do that here either, Okay, so those are the basic, those are the two quantifiers that sort of appear in pretty much any mathematical statement. You just notice the way we say things. I guess we've been talking about sets, so we've been like, I guess one thing I didn't say really is like, now that I think about the set proofs that you've been doing, like, I don't think I was saying like for all A, B, and C, we probably could have been saying that like, given a universal set U, for all A, B, and C subsets of U, A minus B minus C is whatever, whatever like was on the homework. So, so in some ways it's funny with numbers, you tend to like feel this compulsion to quantify. With sets, they're almost like, oh, they're there, but you really probably should. If you want to make precise mathematical statements. Say for every set, for every pair of sets, then this is true. Okay. Yeah. Okay, so we've done that. Examples. Oh, I guess, yeah. So like this is an example, maybe another example, just, have some more examples. I guess we've already seen this. Yeah, there's a couple of just more examples. I mean, what did the homework problems say? We could say like given. So this could be like for any universal set. And for all A, B, C subsets of U, what was it? If C is in as a subset of A, was that what the condition was? What was the homework problem? If C is a subset of A, then something like, is that the union C, something like that, right? So this is a universally, I mean, this is a universal quantifier. I guess there's two universal quantifiers. I'm sort of saying anytime you have a universal set U, and then anytime you have to take three subsets, then you have your. And I mean, you will see people write things like super compactly, even in the book. And I don't love it. Like you'll see people write things like this. For all U, for all A, B, C, subset of U, like that. Here you'll see things like there exists B in Z for all A in Z, A plus B equals A. Like I don't really like, that's almost too shorthandy for me. Like I want to say here, there really should be a such that, or when I'm being brief, I'll write S dot T dot. And also, a lot of books don't do this, but here there should be a comma. It just feels like mathematically correct to me, or grammatically correct to me, that there should be a comma. So I get annoyed when I see statements that are just like symbols, just vomiting symbols onto the page. I mean, the book starts doing, for all A, there exists B. For all C, well, and it's like, it's just not readable, So I much care more about the communication of the ideas than about how you actually write stuff, So notice I have like, I mean, maybe, I don't know if this comma is strictly necessary, probably not grammatically. I don't know if there's any grammarians here, but you do need a comma there, right? And if you're saying there exists something, you need to say there exists something such that what happens, right? So these are kind of points like, don't be too terse. Again, when you're writing on your own, that's fine, but when you're trying to communicate, I mean, you got to sort of figure out your own mathematical style. That's kind of what part of this course is about, developing your sense of what a proof is. But all right, just as another example, I think I had written down is there exists X in R such that X squared equals 2. That's an example, like there is a number that when we square it, it equals 2. This is a true statement. I could give you a similar statement. There exists X in the rationals. Square root of 2 rational. We should prove that it's not. We should prove that sometime soon. But so you can make false and true statements, but like, right? Yeah. I guess also the other place that we've seen this already was when defining sets. Like, we could kind of use E without it being backwards, without you guys think it's backwards E. E is the set of N and Z such that there exists K in Z such that N equals 2K, right? We've already seen things like that. I guess sometimes with their, I gave synonyms for all, like for each and for any, given any, for there exists, you could see there is. Sometimes you'll see for some, like I said, we could also write this as N equals 2K for some K in Z. That's sort of a way of saying some specific. This is also existential right here, right? So if you think about that, that's an existential statement also. It's just reordered. Yeah. Okay, any questions about any of that so far? Now we've already done this in this example 2 up here, but another thing that happens a lot is like mixing quantifiers and order of quantifiers. Like up there, we have a there exists and a for all in the same statement. So for example, yeah, so let's talk about like mixing quantifiers / order of quantifiers. Let's think about like the additive inverse axiom, for example, which is Axiom 6 on this list. Let's think about these two statements. Consider two statements. There exists a B in Z such that for all A in Z, A plus B equals 0, versus for all A in Z, comma, there exists B in Z such that A plus B equals 0. So all I did here was reverse, like swap these, right? All I did was swap the order. So I claim these are very different mathematical statements. One of them is true, one of them is false. Why am I saying that? Let's think about this one. There exists a B. So before I do anything else, I've picked out this B, the special number B, such that for every A plus B equals 0. No matter what A is, it's the same B. Is this true? No, it's not true, right? Like the additive inverse depends on the choice of A. Whereas down here, we pick A first, and then we see there exists a B depending on A. So like this one is dependent on A because it comes after, because we've already quantified A. This is independent of A because we define it first, right? And so the order of this matters. The order of quantifiers here matters. Like this is a false statement. This is a true statement. So the idea being that this statement exists. That's why we call it negative A, because it depends on A, right? But if you look back at the additive identity axiom up there we say that there exists first because it works for every A, right? It's like independent of it. 0 exists independent of the specific number you pick to add to it to get itself. So yeah, that's important. That's an important distinction. Is like that's where the order of quantifiers is important. Like this is okay because once we define A, we can define B in terms of A. But here we define B and then we don't have the luxury then to go back and define B in terms of A. Just sort of the way we've written stuff. I mean, maybe some of it's conventional, but like we're linear thinking beings, so you know. Yeah, so right. So the question is like this is, this is exist. So I'm tempted to say that these are universal in a sort of colloquial sense. This is saying there exists a universal B, or there exists a B that works for all A. And that's not true. Here there exists, but for each A, there's a specific B that works for that A. Okay. So this is sort of the correct additive inverse. This is the additive inverse axiom. This is the additive inverse axiom. Whereas this is sort of nonsense. This doesn't mean anything. This is nonsense. There's no such thing. Now, there are similar statements we could try to make. What if I change this plus to a times? Is it true that there exists a B such that for all A and Z, A times B equals 0? Yeah, what B is it? 0. Yeah, so there are ways to make, you can make statements like that do work for everything, like similar to the additive identity axiom. So yeah, so there's different variations of this. I could give you lots of different variations and ask you like what's true and what's false, Okay. Yeah, so by the way, so here we reverse the quantifiers. We could try to reverse the quantifiers in the additive identity axiom, right? There's no reason not to do that. Okay. Like, right here, but so the additive identity axiom, if we write it again, actually wrote it there, I just erased it, but so additive identity axiom is there exists a B such that for all A plus B equals A, right? What if we reverse the quantifiers here? For all A, there exists a B such that A plus B equals A. Is that still true? For every A, there's a B. You're nodding. Yeah, I mean, then I think this is still true. It just happens to be the same B for every A, right? Still true. Happens to be the same B equals 0 for every A. And so in some sense, you really, like if you want to make the strongest mathematical statement you can, you really should move this back in front because it's independent of A. It's sort of a stronger or more impactful mathematical statement. So if you find yourself in this situation, you might as well move the B, move that there exists in front. Right. I don't know, just trying to point out like different things can happen. You can still have things be true, but just not as like insightfully true or something. Okay. Oh, here's a good one. Let's try some examples where like we try to figure it out maybe together what we would say. So here's another example. Remember, the natural numbers are the positive integers, right? So let's see, how would you translate number n is the positive integers, natural numbers. N has a smallest element. Do you agree with that? There's a smallest natural number. How would we write that down? I'm sort of claiming everything can be put in terms of quantifiers and elements and sets and stuff like that. So how could we write this down in quantifiers? Yeah. I like that, I think, right? There exists a specific A in N. So here, namely, it's going to be namely A equals 1, right? Such that for every B, B is greater than or equal to A. I like the equal to too also, because B could also be equal to A. So it's better to do that. You don't want to like separate out A and then say, I mean, you could say for every other B, for every B not equal to A or something, but then you might as well just write it that way. Good. So nice. Okay. What if we wanted to say, well, okay, so the big thing I want to do now is think about negating statements. So what if we wanted to say N has no largest element? N does not have a largest element. This is really interesting to think about because it's a negative statement. Yeah. Your column? Yes. Yeah. Say for all elements A and N. Does that make sense to people? Like every element you pick, you can find something bigger. That's one way to say there's no largest. Like if I pick 1,000,000, I can do 1,000,000 plus 1, right? So there's something bigger. Good, I like that. So let's see. So for every A or B, I want to make it. I've reversed my sense of A's and B's here, but maybe I should be using M and N or something. M and N. N is greater than or equal to M. So now you're saying for every N in the natural numbers, there exists an M, the natural numbers such that m is greater than n. So given any element, we can find a larger element. Good. Given any number, we can find a larger number. Yeah. Okay. I want to talk in general about how to negate mathematical statements. So we could have done this before we did quantifiers with how do we negate logical statements. Like we sort of talked a little bit about like De Morgan's laws, right? Not P and Q is the same thing as not P or not Q. But we haven't talked about negating implies. We haven't talked about, and now I want to talk about negating quantifiers. So what we could have said first is we could have just said something like, this is not like the statement above, but with the greatest instead of smallest, right? Not there exists m and n actually I want to call this n still. There exists n and n such that for all m and n, m is less than or equal to n. Right, because that's kind of, this would be there is a largest, like this says there is a largest element. It's very similar to what I wrote up here, just with the sign switched. So there exists an n. And so then it's like, well, how are we actually, what's happening when you negate? Like if you just sort of match these up with each other, like this, that, this, that, and this, and that. Yeah, I mean, what does it mean for a statement like this to be false, right? If a for all statement is false, can you sort of say like what it means for a for all statement to be false? How do we show something's false often? What's the simplest thing to do to show a statement is false? Give a counterexample. And it exists, that's like an existence of a counterexample. So if we want this to be false, we need to find an existence. Or going this way, if we want an existence to be false, there doesn't exist any such number, then we need to show for all numbers something's not true, right? So there's a weird thing when you negate mathematical statements, and I'll write this down on the board in a second, but I just want to point at this, gesture at this for a minute first, which is that there's this thing when you negate mathematical statements that you actually switch for alls when there exists. And then now notice this is the negation of this, right? These are negations of each other. Just less than or equal to, if you want to negate that, it becomes greater than. Does that make sense? Yeah, so let me try to write some of that down. So there's a general idea here that like, yeah, if I want to negate a mathematical statement, so P becomes not P, that's easy enough. If we have P and Q, and we negate that, we've said that's the same thing as not P or not Q, right? If we want to negate P or Q, these are these two De Morgan's laws. is the same thing as not P and not Q, right? These are kind of logically, they make sense. If I want neither P nor, like, yeah, somehow the negation of or is nor, and nor, neither nor, right? Neither nor is actually like an and statement in some ways, because you're saying two things. You went from one thing to being true to two things, and then vice versa. So, so that's, you know, these are the different sort of pieces of things that happen. We can talk about implications in a second. I have an example. But for all becomes there exists becomes for all. If I want to be really silly, I can say, maybe I should just make a double-headed arrow. Like these swap, right? Maybe I'll just say these swap with each other. The other thing that swaps with each other are commas and such that's. This is a super goofy thing to think, but I mean, you can really formally negate. You know, if you think about here, this such that became a comma, this comma became a such that. I mean, the comma kind of goes with the for all, and such that kind of goes with the there exists. So if you're going to swap, oh, good, I actually got the right thing on the right side here. The comma goes with the for all. So, a 50-50 shot there. Those swap, right? Right, so we have all of these. And we can do this with various statements, right? Like if we wanted to say, right, so like, let's just do some more examples and then I'll talk about implication. I'm gonna put a couple examples on the board and then let you, I'll let you guys think about it. Yeah. If I could say for every A in Z, there exists a B in Z such that A times B equals 1. The other thing I want to say is, well, actually, take a minute and try to write that out and talk to your neighbors and see what the negation. I mean, and think about whether you believe it, right? This is about something about multiplicative inverses. So write out the negation and see if it makes sense to you as something that's like an explanation for why not every integer has a multiplicative inverse. Actually, sorry, I'm tempted to change this to the rationals because this is still not true. It's very not true for the integers, but I claim it's still not true for the rationals. So, yeah. But talk to your. That's why it's not true for the rationals. Yeah, you're anticipating. But I mean, yeah. So negate it. Talk to your neighbors about how to negate it. All right, so yeah, I think that like if you just kind of play the formal game, it's not that hard to negate it. It's a question of whether it's like you believe that it makes sense, right? Because what is the negation? Someone want to tell me? Someone say it out for me. Well, I hear from Colin a lot. Sorry, I just want to hear from someone else. No, I appreciate it. Someone else want to? Oh yeah.
There exists.
Yeah. Right. So all we did was we switched the for all became a such that, the comma became, the for all became an exists, the comma became a such that, the there exists became a for all, the such that became a comma. I mean, it's really silly that and then the equals becomes a not equals. Make sense? And the question is why, like, I mean, you already said it, but why isn't this true? What's the A that makes this not true? What value? Zero, right? Zero makes this not true. And this is a way to say it, like if you think about putting the A equals 0 in here, for all B and Q, 0 times B is definitely not equal to 1. It's equal to 0. So namely, A equals 0. Good. Oh wait, why did I write the negation down here? Okay. Okay, so that's one. Yeah, you guys seem to be having an interesting discussion about, but there's some subtleties to this that you were arguing over, or? I like arguing.
Like going from one to the other, like if you want to say that the two statements are the same, like
Yeah, right. I guess the negation of this whole thing equals, or is logically equivalent to this whole thing. Yeah, that's a good point. Okay, another one that there's going to be a couple similar problems on the problem set, and I think it's kind of fun to think about because we've talked a lot about like numbers and number theory type stuff, but what about like geometry? So here's an example. Every two lines in the plane intersect in a point. Or I guess, I don't know, I could just say intersect. So this is something from Euclidean geometry, right? Again, is it true or false? False, right? It's, you get a parallel lines. I guess I should have said it depends. If you're in like there are geometries where this is true. And there's like spherical geometries where you see lines do intersect. Okay, first off, how would we mathematize this? So it's funny to think about. There's like, we could say something like R2 is the plane That's sometimes the way people denote like R to the n is like n-dimensional space. We could have L1 and L2 be lines, which would be something. And what would you define a line? It would be some subset of R2 that satisfies some criteria, right? Like, so like L is a line if and only if, or I should say L inside R2 is a line if and only if some condition that you could define. I don't want to get too deep into it. I'm just sort of saying like L in R2 is a line if and only if some condition, but it's a subset. The point is it's a subset. And we can sort of think about how to define what it means to be a line, right? If you wanted to sort of like think about equations or stuff like that, you could sort of imagine what it means to be a line. And so is a line is a specific thing about a specific subset of the plane. Okay, so how would we say, I guess what I'm doing here is mathematize. How would we state this? Well, again, take a couple minutes, think about how you would state this. Again, you don't have to define what a line is. Let's just say you know what a line is. How would you state this mathematically? And then what's the negation? So again, take a couple minutes with your neighbors. I guess well, intersect we know as set intersection, so that actually could work here. There's different ways to answer this, so I'm just curious to see what you guys come up with. I'll even do something else if I want to make it really. Think about this as a subset of the power set of the plane. Set of lines. Because every line is a subset. Yeah, try to chat with someone around you. Sorry, you're not that close to you. Maybe you two can talk.
Because obviously like lines do have an A or B. It doesn't really specify the dimension it's in, so any two lines. Yeah. I didn't do the negation. I'm more than
Yeah.
Tell me if this is sort of correct. So what I was thinking is that there's a set of lines and a set of points where these two lines, I was sort of going with like the algebraic definition. I know it's not wrong. Or not,
Well,
I know it's almost like,
the question of what do you mean by like L of A and L of B? Like that's not very clear.
well, because like, I mean, I'll like, I'm imagining like the line like function notation that like L1 is like x plus 5, and so I'm saying that there's a value. I was thinking about algebraically that there are values where. Oh wait, no.
Yeah, so wouldn't there be like, yeah, like that is, if you're doing it like a function.
Yeah, that was stupid. Yeah.
That's interesting. Yeah, if you want to think about function wise, how you doing? I just realized you have a partner. It's a little, it's kind of weird. Okay, yeah.
I don't know if my thinking is correct yet. What I was thinking is like for all of the lines, two lines, subset of a plane,
Okay.
there exists an A.
Uh-huh.
A can be any number, right? The intersection can be any point, subject to A equals to L1 equals to L2.
So equaling would be like it equals the whole
Because I was trying to think
line.
that two lines intersect at a point, right? So A can be any point in their intersection.
Right. So I would almost want to say this A is a point in R2 and it is actually an element of, because these are subsets.
Right.
So A could be an element of L1 and an element of L2.
Oh,
You know what I mean?
yes.
Yeah.
Okay.
Okay, interesting. So it is sort of funny to try to state all this stuff, right? Like, I mean, I wrote this on the board, like, you know, these are subsets, lines are subsets of R2. You could, you know, again, satisfying some condition about somehow being straight if you want to say it's given by some equation or something. Then I define this scripty L as a set of all lines in R2. And that's a subset of the power set of R2. Think about it, because every line's a subset. It's kind of a funky way to think about things. But then, yeah, so what were people saying? Like what you said.
So I said for all L1, L2 is a subset of R squared.
Yeah, so I would maybe change that to for all L1 and L2 is an element of this scripty L. Because you could say subset of R2, but you'd want to say lines. You'd have to say somewhere that they're lines. You'd have to explicitly say it, just not any subset of R2. Good. Okay, for all L1, L2 in this scripty L.
There exists an A.
Or a point or a subset. A point. So there exists A in R2 such that yeah, I think that's good, right? If we, again, we're sort of assuming we know what a line means. So there exists a point such that it's in both. Anybody else have different sort of answers? You had more like a function type,
Yeah,
right?
I could share mine. So I said for all L1 and L2 in I originally wrote R, but I guess it should be in L. There exists an A in set C such that L1A equals L2.
So you're thinking of L1 and L2 as like functions, like,
Yeah.
and there exists an X in, not in Z, but in R. Like you're basically saying there's an X value you can plug in to get the same Y value.
Yeah. Yeah.
Right. So if you wanted to, I mean, you'd have to define lines in terms of that. And so to say what L1 of A of X means or something, you'd have to say that. There's a slightly more succinct way to say this even. Yeah. Lauren?
Not sure how well this works, but I was thinking that like you have this sort of basic like L1 and L2 are lines, really.
Yeah.
And then you can say that for all like X that are elements of L1, there exists a Y that's an element of L2 such that X equals Y.
So for every X, so if this is L1,
Not for every.
so yeah, so it's not for every X,
Yeah.
but maybe there exists an X and there exists a Y and L2 such that X equals Y or something like that. Yeah, so that's a similar, I mean, that's sort of similar to this. There's even a slightly more succinct way that I could say this. Think about your homework you just been doing.
We said that we use so A that's in L.
Yeah, there exists an A in L1 intersect L2, which is kind of a way of saying, yeah, we could call that just A in L1 intersect L2. We could even say, what do we know about L1 intersect L2 if this is a true statement? Not the empty set. So we could even say for all L1, L2 in this set of lines, L1 intersect L2 is not empty. Right, that's kind of a way to even avoid talking about the point you don't, I mean, not mean empty means like this, you know, means this and means this. So that's kind of interesting. You can almost make it that succinct if you want, right? Again, there's a lot of work being done here that like we know what, like script L knows what a line is, like that we know what a line is and that these are elements of it. Like there's a lot of work being done there. And so then the negation is not too bad, right? What's the negation of this? And just sort of formally. Yeah. Oh yes, such that. Yeah, right. We just negate the statement like that. Exist L1 and L2 in script L such that L1 intersect L2 is empty. Right, and this is true, right? Because there are parallel lines in the plane. So there are lines like that. Yeah.
So can I just double check? So the negation is essentially the opposite of previous sort of.
Yeah, you're just trying to say like, well, if this, what would this mean if this to be false? This to be false, this is no longer universal. It's like there exists something that makes it the claim untrue. This is like saying for all something's true. So if that's false, then there has to exist something that shows it's false. You know? Yeah. So it's like it's kind of funny because there's literally a formal, like, you know, you can just write these in your sleep once you get used to just changing for all. So there exists and commas to such that and beginning statements. But right, you want it to make sense hopefully on some level. Good. Now, the one thing we haven't talked about is negating implication. P implies Q. So, and I wanted to talk about that. I probably could have talked about that before, but how do we negate? And I'll give you an example. But so far, none of these have really been, have had an if then in it so much. So example. For all A, B, and C in the integers, A, B equals A. How did I do this? Those letters the same way I did. AC equals BC. Doesn't really matter, but AC equals BC implies A equals B. So cancellation. We have additive cancellation, which you proved. Is this true? You see some nods and some head shakes. Is there an example for which it's not true? C equals 0, right? So we would have to specify C is not 0 to make this true. So if you want this to be a true statement, you have to say for all of A, B, and C and Z, C not equal to 0, then this is true. Well, how do I negate it? So what's the negation? So I'll do the easy part. There exists an A, B, and C and Z such that, think about what, like if C is 0, what would you have? Like, how would it affect? Like, how would I see this as false? How could I state that there exists something that breaks multiplicative cancellation? Oh, yeah, sorry.
We would just say that like AC equals BC implies B is not equal.
Well, it still implies is a thing. Like, are we saying that because implies is sort of like every time this is true, then this is not true. But I mean, there are values, even if C is 0, there are values of A and B that would make that true. So I don't really like implies here. What other logical connective could work here? We have A, B, and Z such that AC equals BC. What other logical connectives do we have besides implies? There's only a few choices we have. I should erase this. So we have AC equals BC. What else do we have? I feel like I'm sort of must be asking this in a very poor way. What do I mean by logical connective? What are the logical connectives that we have? Do you know what I mean by that word? Give me some other logical connectives besides implies. If I have P, I have Q, what else can I put between them? I can do if and only if. There's more basic ones. Huh? Equal. Okay, we can have equals, I guess. We have and or, right? I think and's the one here. So we have AC equals BC and A is not equal to B. Right? If you think about it, and maybe I should have thought about the truth table, right? What's the truth table for this? It says, when is it false? It's when this is true and this is false, right? And so that's kind of a statement of this being true and this being false. If you think about it like, so, right, let me just remind ourselves. So P and Q, P implies Q. So true, true, false, false, true, false, true, false. And this was true, false, true, true. And I guess what I'm claiming is that this is P and not Q right here. Maybe I need a not Q column, just so not to confuse myself. So not Q is FT, FT. P and not Q. Just smaller. P and not Q. So if we AND the first column and the fourth column together, what do we get? F T FF. Notice this is exactly the opposite of the truth table for that. So not P and not Q. Or maybe I should say not, maybe I should really do not P implies Q. Right? It's the same thing. So those are equal, those are the same. And so really not P implies Q is the same thing as P and not Q. So, and again, I think that should make sense for this example, hopefully. Right, we want the if part to be satisfied, but the then part to fail. I almost want to say P but not Q, but is a kind of and. But is like and not or something. Didn't really, I guess, but isn't used as a logical connective, but we could define it. Makes sense. So the negation of P implies Q is P and not Q. Okay, so in fact, you could really negate any statement now that we've sort of been able to build mathematically. Makes sense? I'll definitely give you some more homework practice with this for next week. Okay. Okay. Whew, got a nice 70 minutes of math. I'm going to do for the last 10 minutes, I guess. No rest for the weary. I thought I'd finish this in like 55 minutes and then have a little break, but we're only 10 minutes away from class, so, into class. So maybe we'll try to finish a couple minutes early. I'm gonna sort of layer in axiomatic number theory. Some here, because I have this goal, like one really nice thing to prove from axioms is unique prime factorization, that every integer can be factored uniquely into primes. And I'm claiming just starting with a set of axioms for the integers, we can actually build all the way up to that, which seems it's a pretty big leap to go from just like these very basic things to saying we can uniquely factor integers into primes. We'll have to define what prime means. But I put this sheet up, this axioms for the integers sheet. And so it has these, like I said, this 1 through 6 that we sort of talked about. But we have lots of sets that satisfy that, right? Like the rationals, the reals, complex numbers, we'll see these modular arithmetic rings we're going to look at. Those all satisfy all of these. There's a couple of additional axioms. We'll have to talk about this well-ordered one later. I mean, we're gonna get to this. This is kind of a weird. It's funny because this is actually something this is similar to something we talked about today, which we said we said n has the smallest element. But let's look at this axiom 7, so that there's this ordering on the integers. So I guess there's this, if you have the integers, we just have like additional multiplication, we have associative, commutative, distributive, additive and multiplicative identities, additive inverses. This is saying that there's a sense of what positive is, this axiom. So let me just sort of write some stuff down. So axiomatic number theory. Okay, so axioms for Z are the ring axioms, which are those sort of like the 0 through 6, plus Z is ordered, and this other axiom that says Z is well ordered, which again we'll come back to. But let's focus on this one. This one this defines what it means to be positive. I'll even just say about this, we'll get to it later, but you might be really like curious. The thing that's special about the integers is there's always a next one. You know, after 1, there's 2, after 2, there's 3. That's not true for like the rational numbers. What's the first rational number after 7/13? I don't nobody knows. It's not, doesn't make you can get as close to 7/13 as you want with rational. So like there should be some axiom that somehow specifies the like that you can list the integers in a nice way, or that like so that there's a nice spacing in the integers. And I claim, even though that looks very strange or not connected at all, that this actually the axiom, the well-ordering principle is what gives you that. But this defines positive. So what it says is there exists a subset of the integers called the natural numbers. Not empty. It's important that it's not empty. You could have the set just containing 0, and that actually satisfies all the axioms. If you that like the set just containing 0, set like 0 plus 0 is 0, 0 times 0 is 0. It's sort of silly, but that satisfies all the axioms. 1 could equal 0 in that set. So you have to be careful. So we need to say it's not empty, such that, and then there's these 2 conditions. I mean, they're on screen, but we have closure. So for all A and B in the natural numbers, comma, A plus B and A times B are still in this set. So it's closed, right? That's closure. And the other thing you need to do is somehow state that every number is like positive, negative, or 0. You need what's called trichotomy. You may have heard that before, trichotomy. So that's the first condition. And yeah, the second condition is for every A, for all A in the integers, basically every integer is related to the natural numbers in this following way. It's either in the natural numbers, or it's 0, or its additive inverse is in the natural numbers, right? So for every A and Z, I could state that as like an XOR or something like that, exclusive OR. But maybe I will state that as an XOR. We want to be very logical about it. A is in N. Have I said XOR before? XOR is exclusive OR, which means it's like one or the other is true, but not both. A equals 0. Actually, you know, I have to be a little careful because there's a difference between pairwise XOR and like triple XOR. I'll just say exactly one is true. So every integer is either in the natural numbers, it equals 0, or the additive inverse is in the natural numbers. So I'm referring, we have an additive inverse axiom, so we've defined 0, so I know what 0 is. We've defined additive inverses, so I know what that is. So this is an axiomatic way of stating somehow that there's positive. Yeah. Why? That's a good question. I claim it does fail one of those 2. Yeah, why aren't the negative numbers another choice for this? So does it satisfy trichotomy, right? Does it satisfy the first bullet point? If you add 2 negative numbers, you get a negative number, but if you multiply 2 negative numbers, you leave the set. So it's not true for, so that's a good point though. Those are good things to think about. Like, why can't this work for someone? Like, why is this a good axiom? There's a lot of good, yeah, that's good. So this is called trichotomy. By the way, these aren't the only way to axiomatize the integers. This is sort of how I learned it, and I really like how it works. But I also, we can define, wait, so I have this properties of the integers, which is something we're going to come back to. Hold on a sec. So, right, okay, so let me switch the share to this. So if you look at this sheet, which is properties of the integers, we've actually done a bunch of these first ones. We did cancellation addition. We did 2 and 3. It's interesting to think about 4, 5, and 6. Maybe I'll ask you to prove these at some point, or we'll prove them. Divisibility we'll come back to. That's a very important foundational thing with integers, like what it means for one integer to divide another, which you might believe means that like A divides B means A times, there's a K, so A times K equals B, you know. But then ordering is this thing here. So once we have this axiom, we can define the greater than symbol and the less than symbol. I mean, we could define the less than symbol as just the opposite of the greater than symbol. We can define the greater than symbol, right? And one way to define it, I mean, this is sort of a nice way to define it, basically, like, if you go with the number line, right, this says A is farther to the right on the number line than B. And so you can get from B to A by adding a positive integer. Okay, so I'll write that down too, just to. But then like there's stuff to start proving, and we can start next time proving a few of these, and I'll put some on the homework too. But let me just write this on the board so you guys write it down. So once we have this axiom, because the axiom I called it Z is ordered, so this is what the ordering is. We can define ordering on the integers. So the definition is sort of for, or given, I guess you could say for all, given A and B and Z, we say A is greater than B if and only if there exists a K in the natural numbers. That's very important, that it's in the natural numbers, such that A equals B plus K. Does that make sense? 3 is greater than -1 because -1 plus 4 equals 3. Okay. And then we can prove properties of ordering. But we're out of time, so we'll have to do that next time. So you can think about some of these and see if they're true and if you believe them and stuff. Okay. Cool. Good. All right. We did quantifiers, a little bit of this. Problem sets due tonight. I forgot to post it on Gradescope until last night. Sorry. People should remind me. If you go to, just the thing I'm really absent-minded about is like, I'll write the problem set and post it to our website, and then I'll forget to like make the Gradescope so you can actually submit it. So if you ever try to look and see that there's just like send me an email like, dude, Gradescope. I'll be like, okay. You know, you've been with me. Although we weren't on Gradescope. Like, all right, guys. Thank you. That was fun. Math is fun. I have office hours 2:30 to 4 today if you want to stop by. I hope maybe people went to Gabriel last night. Oh, good. Oh yeah, you guys went last week too, right? So were you the only ones? Okay, yeah, we need more people to join. Gabriel is very helpful. He knows this stuff. Yeah, take care. Wait, is your name Ansh? No, what's your name? Ansh?
Yeah.
Okay. I'm just trying to learn the names.
Oh, yeah.
And I wanted to make sure. And I'd seen I was like looking at the, yeah, so you can. I was looking at the picture, the roster, photo roster, yeah.
Do you have time to look at my?
I have to teach again in 10 minutes in this room. Oh,
Just want to know